This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of our series, How AI Actually Works, The Complete Picture. In this episode titled, Neural Networks, Digital Brains Explained Simply, we're going to break down the basic structure of neural networks and demystify how these digital brains function. So whether you're curious about how they learn, or simply want to understand the buzz, let's dive in. Right now, a neural network is finishing your sentences in email, spotting faces in your photos, and steering cars down real streets, and most people can't explain how it thinks. Let's step inside this digital brain and unravel how something so simple becomes so eerily smart. Neural networks quietly sit behind tools you use every day, but their real shock factor is scale. GPT-3, for example, was tuned with about 175 billion adjustable dials after being fed hundreds of billions of words. That's why it can jump from drafting emails to writing code without being explicitly told how to do either. Vision systems show the same story. Image classifiers went from missing the object 1 in 4 times in 2011 to beating most humans on benchmarks by 2017. And yet, under the hood, each neuron still does almost nothing on its own. Stack enough of them, train long enough on the right hardware, and you get systems that can translate languages, recommend movies, and even outplay world champions in Go while checking far fewer moves than old-school engines. The magic isn't a new kind of thinking. It's what happens when simple pieces collide at massive scale. Behind the buzzwords, the key question is, what are these systems actually doing when they learn? At training time, they're fed oceans of labeled examples: cat versus dog photos, translated sentences, recorded moves from expert Go players. During this process, they constantly adjust billions of tiny numeric settings so that their outputs better match those examples. Over time, they stop memorizing and start spotting regularities, edges that often outline objects, word patterns that signal sentiment, move sequences that usually lead to a win. That's why, after training, they can tackle fresh inputs they've never seen before. So what's actually happening inside, between input goes in and answer comes out? Start at the front door, the input layer. For text, that might be a stream of numbers representing words. For images, grids of pixel intensities. These numbers get passed into the first, hidden layer, where each artificial neuron performs just 2 things. It mixes the inputs with its own private set of weights, then decides how strongly to fire based on that mix. Crucially, no single neuron knows what a cat, a noun, or a winning Go move is. Instead, each one becomes sensitive to a tiny, abstract pattern, a particular edge orientation, a specific word context, a local board shape. Early layers tend to react to very primitive signals. Deeper layers respond to combinations of those signals, textures, object parts, sentence structures, until the final layers work with fairly high-level concepts that are useful for the task. The power comes from composition. Each layer transforms the data into a new representation that makes the next layer's job a bit easier. In practice, this means the network learns its own internal features automatically. Before deep learning, humans had to hand-design these features, like edge detectors or syntactic rules, which often broke when data shifted slightly. Different architectures push this idea in specialized directions. Convolutional networks, CNNs, reuse the same tiny detector across an entire image, which is why they scale so well for vision tasks like ImageNet. Recurrent and transformer models handle sequences, tracking how earlier elements change the meaning of later ones, which is critical for language and time series. Actor-critic and value networks, in systems like AlphaGo, estimate the quality of positions or actions directly, replacing brute force search with learned intuition. Underneath, it's all linear algebra, matrix multiplications and nonlinear activations, repeated at massive scale on GPUs, designed to crank through those operations efficiently. During inference, after training is done, The network is just running this fixed, layered computation, now tuned so its internal representations line up with patterns it previously discovered. Think of where these digital brains quietly surface in daily life. A photo app that auto-groups pictures of the same friend isn't just tagging faces. Deeper inside, one layer might respond strongly to round glasses, another to curly hair, another to jawline shape. Together, they form a kind of numerical portrait that stays consistent even when lighting, angle, or hairstyle changes. Voice assistants show a different flavor. One part of the model learns to map noisy audio into text. Another, stacked on top, focuses on intent. Is set an alarm a request, or part of a story you're telling? In fraud detection, banks feed streams of transaction data through networks that grow a sense of normal spending patterns and flag odd combinations. A small test charge in one country, followed by luxury purchases elsewhere minutes later. Training these systems is like baking a multi-layer cake. Change ingredients at the bottom, raw data, objective, and everything above it rebalances, yielding a new recipe for recognizing patterns, whether in pixels, payments, or spoken requests. As these systems spread, expect them to slip into boring places first, triaging medical scans, drafting contracts, optimizing power grids. Then the questions get harder. Who's accountable when an AI-assisted diagnosis is wrong? How do we prove a model isn't quietly biased against a neighborhood or dialect? Your future doctor, lawyer, or teacher may rely on tools you can't easily inspect, pushing regulators to demand clearer flight recorders for algorithmic decisions. We're still in the early internet dial-up phase of these systems. Next comes wiring them into tools you already trust, spreadsheets that forecast like seasoned analysts, cameras that notice safety hazards as casually as clutter on a desk. The hard part isn't just, can it work? But how do we steer it? That's where curiosity now matters more than code. Before next week, ask yourself, 1. If I had to explain how a neural network's layers and weights work using only a real-life example from my day, like choosing a meal, recognizing a friend's face, or sorting emails, what story would I tell? And where in that story does training actually happen? 2. Looking at one decision I made today, can I trace it like a tiny neural net? What inputs did I notice? What hidden rules, biases, or habits transformed them? And what output did I choose? 3. If I treated one habit I want to change as a neural network being retrained, what specific training data, situations, feedback, or practice reps could I feed it this week to nudge its weights in a better direction? This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!